Okay, so let us continue our discussion. So, today we are going to investigate response due to support motion. Now, if you recall, we derived the expression for dynamic amplification in the previous class. So, we have this combination of mass spring and dashpot. Now, in that case, so mass, stiffness and damping and x of t, where dynamic amplification dmf, which is also defined by this non-dimensional one. So, square root of 1 minus r square whole square plus twice eta r. What does it mean? So, if this displacement is due to a forcing function which is sinusoidal, then for that we can find out that sinusoidal force, its amplitude, and from that we can find out the static deformation. And then if we multiply that static deformation by this non-dimensional number, we get the dynamic response. Today we are going to slightly modify the problem statement. So, what we are going to do is instead of applying force at this mass, so what we have this support, it is moving x s of t. Now, there are different examples of this type of problem. For example, if you have a building and then it experiences support motion like earthquake. So, let us investigate if we have this x of t, and in this case x of s of t, where this subscript s stands for support motion. So, this displacement is given by x naught sin lambda t. Then our task is to find out this response quantity x of t. So, for that again what we do, we first draw the free body diagram of the mass. Then in this case there will be inertia force. What is the magnitude of this inertia force? M x double dot. There will be a spring force and a damping force. So, the spring force is x minus x s, that is the net deformation multiplied by the stiffness k. Similarly, the damping force c times x dot minus x dash dot. Now, once we draw the free body diagram, then we can easily write down the equation of motion. So, in this case the equation of motion is mx double dot plus cx dot plus cx dot minus xs dot plus k times x minus xs is equal to 0. So, we can modify this expression, and what we have mx double dot plus cx dot plus kx is equal to cxs dot plus kxs. So, this new quantity is actually the applied force that is causing the vibration in the structure. Now, we know xs, so we can easily find out what is xs dot of t, and that is x naught lambda cos lambda t. Similarly, xs double dot of t is equal to minus x naught lambda square sine lambda t. So, we have the support displacement and velocity, and then we can find out what is the effective force. In this case, effective force is nothing but C xs dot plus K xs, and we can put the expression. So, what we have is C, then x naught lambda cos lambda t plus K x naught sin lambda t. And then we can combine and then write down in the compact form. So, it will be f naught sin lambda t plus beta. So, what we do? We consider this C x naught lambda as say sin beta, and then this part also we assume it to be cosine, and then we can write down what is the expression for f naught. F naught will be square root of C x naught lambda whole square plus K x naught whole square. Then we can further simplify, you can take this x naught out, and then inside we will have C square lambda square plus K square. Now, in place of C we can further modify. So, what we have is x naught square root of, in place of C we can write twice eta m omega n times lambda whole square plus K square. Now, if we take K square out, so what we have x naught K square root of, then twice eta m omega n, then lambda divided by K plus 1. So, this will be whole square. Now, obviously, in place of K we can write m omega n square. Obviously, this m will get cancelled and this omega n and square will get cancelled. So, what we have x naught K, then square root of 1 plus, we have twice eta, and lambda by omega n is r, that is the frequency ratio. So, square of that. So, this is the expression for f naught. Now, similarly, this beta also you can write the expression for beta. So, beta will be, let me just write here. So, tan beta will be equal to C lambda divided by K. Now, once we find out what is the effective force, so in place of this we can now write f naught sin lambda t plus beta. So, obviously, what we see, we started with a support motion problem, and effectively what we get, x of t, that is the absolute displacement x of t, is due to a sinusoidal force, and the expression for that effective force we have already evaluated. Now, for this problem we can easily write down what will be the response, and then response will be f naught divided by K. If you recall, that is the static deformation, then sin lambda t plus beta minus theta. So, there will be a phase lag divided by 1 minus r square whole square plus twice eta r whole square. Right. So, this theta, we have already derived the expression for theta, you refer previous class note, you will get it. Now, Note this x of t, it is the absolute deformation. Now, the expression for absolute deformation also we have. Now, in place of f naught, we can now write down the expression that we have derived here. So, what we will get x of t, in place of f naught, if we write x naught k, that k will get cancelled. So, we will have x naught, then square root of 1 plus twice eta r whole square, and then sine lambda t plus beta minus theta, and then divided by square root of 1 minus r square whole square plus twice eta r whole square. So, that is the expression we have for absolute deformation, and this deformation is due to a sinusoidal support motion whose frequency is lambda. Now, if we further consider the expression, so what we have x of t, let me just write it down and then I will explain. X naught square root of 1 plus twice eta r whole square divided by square root of 1 minus r square whole square plus twice eta r whole square times sine lambda t plus beta minus theta. In fact, in place of this beta minus theta, you can introduce a different combined one. So, that we can represent it in terms of say phi. Now, if we consider the amplitude of this motion, so this part is the amplitude, and then if we find out x of t divided by x naught, what is that? This is the amplitude of the support motion. Now, that ratio is given by 1 plus twice eta r whole square divided by 1 minus r square whole square plus twice eta r whole square, then sine lambda t plus phi. Now, if you consider the amplitude of this, obviously you will on the right hand side you will have, so this quantity, and this is called the transmissibility. Now, this expression transmissibility, again it is a non-dimensional number. If you look at the expression, it has r, that is the frequency ratio, and eta, that is the critical damping ratio. Now, let us investigate if r equal to 0, then what happens? If r equal to 0, obviously you will see Tr, that is the transmissibility, is equal to 1. So, no matter what is the value of eta, the moment r is 0, that means this transmissibility will start from a unit value. Now, let us also investigate if r is equal to square root of 2, then what happens to Tr. So, let us investigate. So, Tr will be square root of 1 plus twice eta, then r is square root of 2 whole square divided by 1 minus square root of 2 whole square, and then plus twice eta square root of 2 whole square, and then the complete thing will be under square root. So, what we have square root of 1 plus, so 2 square 4 multiplied by 2, so 8 eta divided by square root of, now this square root of 2, if you square it, then you will have 2, 1 minus 2 is 1, then again if you square, so that will get 1, and then here again you will have 8 eta. So, the value is again 1.0. So, you can easily identify at r equal to 0, transmissibility is 1. Not only that, at r equal to square root of 2, no matter what is the value of this critical damping ratio, again the transmissibility is 1. Now, if we plot that curve, so on the x axis we have r and y axis we have dr, and then this is r equal to 1, which actually represents resonance. And then again say this is also the horizontal line representing T r equal to 1. So, this is 1.0. Now, obviously, when eta is 0 and r equal to 1, so you will have a plot like this. And this value again at this point, the magnitude of T r is 1. So, this is r equal to square root of 2. So, this is eta equal to 0. Now, if you have a finite eta, so what will happen? It will go up and then cross this resonance, and then again it will meet this point and then go like this. And as we increase damping, obviously it will cross the same point. Now, obviously on the left hand side, this is how the eta increases from 0 value, and on the right hand side of r equal to 0.2, this is the direction where eta increases as we increase it from 0 value, right. So, that is the qualitative plot of this transmissibility. When we will have a session dedicated for MATLAB, then we will actually plot this in a better way. We will write the equations in MATLAB and then plot it, and we will see the same nature we will get. But for the time being, to understand the nature of the transmissibility, so we refer this plot, and it clearly tells that these 2 points are equal to 1 and then are equal to square root of 2. This is the 2 most important point. In case of dynamic magnification, the behavior was not like what we observe here in this plot of transmissibility. Okay. Now, recall the equation in this case. What we have? We have m x double dot plus c x dot minus x s dot plus k x minus x s is equal to 0, right. Now, let us imagine a new variable u, which is the relative deformation, and that is equal to x minus x s. So, u is the relative deformation with respect to support. So, in this case the mass moves by an amount of u of t, right. So, then u dot is equal to x dot minus x s dot. So, in that case what we will get m in place of x double dot. So, if I write down u double dot, it will be x double dot minus x s double dot. So, obviously it gives you x double dot is equal to u double dot plus x s double dot. Now, if you do that, what we have, we can write it down directly. So, we have m u double dot plus c u dot plus k u is equal to minus m x double dot. So, this is again the same equation, but in this case what we have is the relative deformation u. So, m u double dot plus c u dot plus k u is equal to minus m times x s double dot. We have already derived the expression, here you have. So, that is minus x naught lambda squared sin lambda t. Okay. So, minus so it will get plus minus x naught lambda square sin lambda t. So, this is again the effective force but in this case what we have is the relative deformation with respect to support. Now, for this problem also we can write down what is u of t, and u of t will be the amplitude of the force. In this case you have m x naught lambda square divided by k times sin lambda t minus theta divided by square root of 1 minus r square whole square plus twice eta r whole square. Now, if you look at this expression m x naught lambda square by k, you can simplify this because in place of k you can write m x naught lambda square then m omega n square. So, this m will get cancelled. So, what we have x naught, then lambda by omega n is r. So, we have r square. So, we can further modify this expression. So, what we have is x naught r square. Now, if you look at the amplitude of u, what is that quantity? It is x naught r square divided by 1 minus r square whole square plus twice eta r whole square. Now, again if you take the ratio of ut's amplitude and the mean deformation of the support, you have this is the expression. So, the same problem we have solved in terms of absolute deformation and as well as relative deformation. We will use this information further as we progress, but for the time being what we have, if we excite the support using harmonic function, then for that we have derived the expression for transmissibility and we can write down the expression for absolute deformation as well as relative deformation. Now, imagine if we have a mass and let us change the orientation. So, it is supported by a spring and a dashpot. So, this is the mass and obviously the degrees of freedom is now in this direction x of t. Our task is to find out the force transmitted to the foundation. And the applied force here f of t is again sinusoidal. So, we have f naught sin lambda t. So, if we look at the spring damper arrangement, it is actually the spring and the damper that is connected to the foundation. Now, this is a very common problem. So, if you have an industrial structure and there if you want to place a machine, normally machines rotate with certain frequency, it vibrates with that driving frequency what is here lambda. Then we need to design the machine foundation because it should take the force and that is the force transmitted to the foundation. Now, what is x of t? We can easily write down it is f naught divided by k times sin lambda t minus theta, then square root of 1 minus r square whole square plus twice eta r whole square. That is the expression for absolute deformation this mass is going to experience. Now, it is also steady state response. So, steady state response. Obviously, if you have a machine over a foundation, when you start that machine there will be a transient part, but as time progresses then obviously it will settle down with its steady state vibration. So, for the time being we consider steady state vibration. And what is the force transmitted? So, if I write down force transmitted is f of t, then that force we can quantify. So, stiffness force k times x plus the damping force c x dot. That is the force transmitted to the foundation. You can easily look at the foundation and identify the forces. Now, if we write the expression, so k times these are functions of time. So, I can write down the expression of x of t. So, what we have is in place of x of t we have f naught by k sin lambda t minus theta divided by the third bracketed term. I am just not writing it, and then plus c times your lambda, then f naught by k, then cos lambda t minus theta divided by the term in the denominator. Now, again we can combine this expression. So, what we can do, f naught by k is what? This is x naught, that is the static deformation. So, what we can do, we can take this out and then the third bracketed term. Then what we have inside is k sin lambda t minus theta plus c lambda cos lambda t minus theta. And this expression again we can further simplify. So, what we have x naught divided by the term in the denominators, and we can write this expression. So, this will be square root of k square plus c lambda square, and then we will have sine lambda t minus say plus beta minus theta. What is tan beta? This is c lambda by k, and that is equal to twice eta r. We have already derived this quantity. So, you can see again the force transmitted to the foundation is again a sinusoidal force when the machine vibrates in its steady state, and the amplitude you can easily quantify, that is the amplitude. Now, so if we write down the amplitude, so what we have x naught square root of this k square plus c lambda square, we can actually take this k out, then it will be 1 plus twice eta r whole square, and then we will have 1 minus r square whole square plus twice eta r whole square. Now, this is the amplitude of the force transmitted. So, if we continue, so what we have is a t. Let me just quickly write it and then we will see. So, you will have x naught k square root of 1 plus twice eta r whole square divided by 1 minus r square whole square plus twice eta r whole square. Now, what is this quantity x naught times k? This is nothing but our f naught. So, now if we find out the ratio of transmitted force to its amplitude. So, what we have on the right hand side is again 1 plus twice eta r whole square divided by square root of 1 minus r square whole square plus twice eta r whole square. So, when we design a foundation for a machine, we have to actually find out this non-dimensional number. What does it mean? If the machine has a external force applied to it with a static amplitude or constant amplitude f naught, then that should be multiplied by this factor to find out the amplitude of the force transmitted to the foundation. So, if you design the foundation, then obviously you have to find out this force before you start your design. And that gives us the complete idea of when a structure vibrates under support motion, or if we have a sinusoidal force, how much force is transmitted to the foundation. Now, you can see this Tr, it is a function of what? It is a function of r and eta. So, while designing, we have to be careful about these parameters, and we have to design the foundation in such a way it can withstand this force. And remember, this r actually is the frequency ratio. So, the machine can operate at higher frequency. Obviously, as you increase, we have already plotted, you have to be careful about the nature of that expression for TR. Nevertheless, at r equal to 0 and equal to square root of 2, no matter what is the value of damping, we will always have a transmissibility which is equal to 1. Now, this theory can be applied, and one of the application is seismic measurements. So, during earthquake, you know, ground starts vibrating, and that motion we can record, and the instrument is called seismograph. How does it work? So, basically it has a structure like this. So, this is a hard casing, inside that we have the seismograph. So, we have a mass here, and then there is a damper, and then there is a spring, and in this mass a pointer is connected, and there is a scale here, so what is the degrees of freedom of this mass? It can actually vibrate in this vertical direction. So, if there is a ground motion, say x of s, obviously what will happen? This pointer will start moving in the vertical direction depending upon the stiffness and damping characteristics of this instrument. Now, this movement of this pointer is recorded, and that movement we actually can represent using this relative deformation, which is x minus xs. We have already derived this expression for this quantity, and we will see in a minute how we can use that theory to measure the vibration. So, this is the schematic diagram of a seismic measuring instrument. Now, using this instrument, we can measure the displacement, also the acceleration. So, the ground displacement or acceleration, both we can measure depending upon the tuning of this instrument. Now, if we find out what is the peak relative response, you can easily tell me that it is u divided by x s naught, and this quantity is what? This quantity we have already derived. If you recall, I told you we will use this relation. So, let me see where it is here. So, this relation we will use. So, what is that quantity? It is r square divided by square root of 1 minus r square whole square plus twice eta r whole square. So, that is the expression for peak relative response. Now, if you plot this, so on the x axis we have r frequency ratio, and y axis we plot u divided by x s naught. Then again we have r equal to 1, that is resonance. So, this is r equal to 1, and when r equal to 0, obviously this quantity will be 0. So, this starts from 0. and then goes like this. So, if you have so, this is eta equal to 0, and then as eta increases. So, we have this. So, this is for eta equal to 1. So, what you can notice from this schematic diagram is that as we increase R, after certain range the response is almost constant. So, for R greater than 1.0 and if you have eta equal to 0.5 onward, then for that response is almost constant. Now, the response of a properly damped instrument actually is if you look at this response and then if it becomes constant, then in that case what happens? The response, relative response u is directly proportional to the base displacement. Okay. So, under this condition we can use this as a displacement measuring device, right. So, this condition actually tells us that the relative displacement is proportional to the base displacement. Now, if we just reinvestigate the support motion problem. So, what we have, the acceleration is represented by this quantity, right. And then dynamic magnification under this case will be what? It will be u divided by m x double dot divided by k, and that is equal to 1 by square root of 1 minus r square whole square plus twice eta r whole square. Now, under this condition, if we just investigate if say eta equal to 0.7 it is, and then r is in between 0 to 0.6, obviously then what happens? You can see the relative displacement u is actually proportional to, so the response is proportional to base acceleration. So, under this condition, this instrument behaves as a accelerometer. Now, if we tune the parameters of this instrument in such a way that we satisfy these conditions, then you can actually use this as a measuring device, and just by tuning we can measure the displacement or accelerations. So, that is how it works. So, the theory that we have developed today, it is applicable for seismic measurements. So, as we move further in this course, we will see if we have a arbitrary record. What we do normally in case of earthquake, we measure the accelerations. So, we will have this support motion x s double dot of t that is measured, and if you look at the nature of an earthquake. So, it is a random signal. So, this is t and this is x s double dot of t. So, under this kind of arbitrary signal, how to find out the response, that we will investigate, but for the time being today the theory that we have developed for support motion problem, where the support motion is modeled by sinusoids, then under that situation we have derived the expressions for the response. It may be absolute, it may be relative, and then again if you have a machine, then we have derived the expression for the force transmitted to the foundation. What is the nature of that force, that we have investigated, and then finally how we can use that theory to measure the seismic signals, that also we have gone through. So, with that, let us close here. In the next class we will solve some problem and then we will see how we can apply this theory for our structural vibration problems. Thank you.